Hello, good afternoon to all of you. I hope all of you are doing well. So in today's class, we're going to discuss about a few of the important concepts related to function-oriented design. Now, in the previous class, we've learned about a function-oriented approach, its characteristics, and its major limitations. We've learned about data flow diagram, we've learned about context diagram, we've learned about the various notations that are used, we've learned about data flow rules. Now in today's class we're going to learn about the associated concepts with function-oriented design. So the first concept that we are going to discuss is synchronous and asynchronous process interaction. So process may interact with each other synchronously or asynchronously. So synchronous interaction basically means in-time interaction between the processes, right? Okay. Whereas asynchronous basically means they do not interact in time and respond to each other at different timestamps. So an example, a telephonic call would be a best example for synchronous interaction, where you have a caller and a callee. So as the signal generated by the caller, the callee responds to the signal, right? So as the information is produced, the information is readily consumed in time. So in such situations, what I need not do is I need not implement a data store. Whereas in case of asynchronous interaction, the best example would be communicating with your friend through your email services. So you send an email now to your friend, which may be consumed at a later point in time. So for that, what we need is we need a data store to be implemented. Okay. So that is the basic distinction between synchronous and asynchronous processes. So a synchronous process is invoked by request and response operation, where the result of the process is returned by the caller immediately via this operation. So it takes place in time. Whereas in case of asynchronous process is invoked by one-way operation, and the result and any fault is returned by invoking the other one-way operation. The process results in returning the process results in return to result is returned to the caller via a callback operation. So it happens at different time stamps. So that is a typical example of typical distinction between synchronous and asynchronous interaction, right? Again. So it's given here. So a typical example of synchronous process would be a telephone call, and asynchronous process would be postal services. Now, another important aspect of a important concept related to function-oriented design that's called as data dictionary. Now, data dictionary or a metadata repository, right, is a centralized repository of information about data, such as that contains information such as meaning, relationship to other data, origin, usage, and format. Now, data store is very much essential. Data store is a mechanism of creating a repository which holds the meaning of the data, which holds the relationship of the data, origin, usage, and the format of the data, right? So it provides definition for all the elements in this system, which includes meaning of the data flow and the stores in the data flow diagram, right? Again, composition of the data flow, right? Again, so again, composition of the data store, right? Details of the relationship between the various entities. So just see, these are the important aspects that a data dictionary tries to emphasize upon. That is meaning of the data and the data store, composition of the data, composition of the data store, and details of the relationship. So what does it basically tries to provide is it basically tries to provide a uniform and a standard terminology for all the items that are present in the data flow diagram. So what we have learned about is we have learned about what is a data store, right? Again, what is the importance of the data store and what does it has in it. Now there are various data flow notations that we can follow. So equals to represents equivalence or is composed of, right? Plus and a pair of parentheses optional, pair of curly braces iteration, pair of square brackets selection, and then comments and identifier for store, right? Again, and then selection between different choices in case of alternatives, right? Again, so here what we have is we have equivalence, we have composition and composed of, right? Optional, iteration, selection, comments at the rate of, right, and or, right. So these are the various notations that are used for defining data in case of data dictionary. Now name, so you have courtesy title plus first name, optional middle name, and last name. So that is the way how a name is defined, you see. So you have composed of and, right, composed of. So name is composed of courtesy title, Mr., Mrs., Doctor, Professor, right? Okay. Then first name, optional middle name, and last name. Courtesy name can be any of this, right? Mr. or Miss or Mrs. or Miss or Doctor or Professor. And first name can be any legal character. Middle name can be any legal character. Last name can be any legal character. Now, legal character can be either A to Z or small a to Z, right? Okay. So just see an iteration of this. So the repetition of all of these characters may be any legal character. So you see, this is what this is what data dictionary is, and what are the notations for defining data and how to define data. So this is a typical example. So it very often comes in the examination, a question pertaining to how to define data using the various notations, right? Now, next, the important thing that we're going to study is we're going to study structured chart. So, structured chart is a organizational chart that is capable of representing the system in terms of modules, right? Okay. So, a structured chart in software engineering and organizational theory is a chart which shows the breakdown of the configuration the configuration of the system to the lowest level of abstraction. Okay. So what it tries to do, it tries to decompose the system into the lowest level of abstraction over a series of decomposition. So at the first level, what we have is we have the root node that represents the system, and in subsequent levels we have the modules with a further decomposition sub-modules. So this chart is used in structured programming to arrange the program modules in a tree-like structure, right? Again. So the tree structure visualizes the relationship between different modules. So it visualizes the invocation relationship between different modules. So it is interpreted in a top-down manner, where it organizes the system as a collection of modules in a top-down manner, right? So the connection between the different modules shows the invocation relationship between the different modules, right? Okay. And so the lines represent right, and the lines represent the connection or the ownership between activities and sub-activities as they are used in the organizational chart. So it basically represents the invocation relationship, right? So a structured chart basically represents the size and the complexity of the system, a number of readably identifiable functions and modules, right? Within each function, whether each identifiable function is manageable entity or should be further decomposed or broken down into smaller components. So that is what a structure chart is capable of depicting. It depicts the size and the complexity of the system. It depicts the number of identifiable functions and the modules within each process. Whether each module, each function is a atomic function or it has to be further decomposed. So that is what it's capable of representing. So these are some of the important notations. So this is used for import data. This is for export data. This is for import and export data. This is major decision. This is repetition. This is a module. This is a module invocation. This is module invocation, or this is subroutine, right? Again, and data flow. So we'll try to understand data flow diagram and structure chart with the help of an example. So we'll take up an example and we'll try to understand how to create a data flow diagram and how to represent it suitably using a structured chart. So in this particular chapter, what we learned about is we learned about function-oriented design. We learned about data flow diagram. We learned about data flow notations, and then we have learned about different data flow rules. We've learned about the various ways in which the elements of the program can interact. Then we discussed few of the important concepts. We discussed synchronous and asynchronous interaction. We discussed data dictionary. We've learned about what are the various notations in the data dictionary. We try to understand it with the help of an example. Then we discuss what is a structured chart. Then we discuss the importance of the structured chart as well as some of the notations. So in the upcoming classes, what you're going to learn about is we're going to learn about in more detail about data flow diagram and the structure chart with the help of an example, right? Again, now for us as a software engineer, it's very important to identify transformation processes from data flow diagram, how to transform processes from data flow diagram to structured chart, right? So now what we tend to do is we tend to basically identify three important uh, aspects of the system, that is afferent, central transform, and efferent, that we have already learned in the previous chapter. So afferent basically means any module that is capable of converting physical form to logical form. Central transform basically means any module that's capable of converting data from one logical form to another logical form, and efferent basically means logical back to physical form. So whenever we are trying to transform a data flow diagram into a structured chart, all the modules that are capable of performing this operation, right, that is physical to logical, is grouped into one. Logical to logical is grouped into another, and logical back to physical is grouped into the third one, right? So that's called as transformation analysis. So identify the system. So the various steps that are involved in transformation of data flow diagram into structured chart are: identify system processing transformation, identify input transformation, and identify output transformation. So identify system processing transformations are transformation that converts a logical data into logical data of another form. Input data transformation is that takes in physical data and converts into logical form, and output data transformation is transformation that converts logical data back to physical data. So this is very much important. So thank you very much. Have a good day.